So up until now, we have not had a product rule or a quotient rule for taking the derivative, meaning if we had a quotient or a product, we were required to rewrite it so it wasn't a product or it wasn't a quotient. For example, if we came across this f of x, this function, equals x times the quantity x squared plus 4, and we wanted to take the derivative of it, we had to distribute the x, rewrite the function so that it became x cubed plus 4x, and then take its derivative, because we do know how to take the derivative of a sum. So we take the derivative of the first part, put the 3 out in front, subtract 1 from the exponent, plus the answer for the derivative of this, which is 4 times the derivative of x to the first. You put the 1 out in front, multiply by it, and then subtract 1 from the exponent, which ends up to be x to the 0. And we know x to the 0 is just 1. So the derivative is 3x squared plus 4. And I wrote 3x cubed. Okay, 3x squared plus 4. Well, we do have products that we can't actually multiply together, so there is a necessity for a product rule. And here is the product rule. There are two ways to write it, either with this cumbersome f of x, g of x notation, or u times v. So if we look at the u times v notation, u stands for the first function, anything with an x in it, and v stands for the second function, anything with an x in it, or any variable. But not just like 4x, okay? We wouldn't use the product rule for a constant times a variable. We would use the product rule for something with a variable in it times something else with a variable in it. And the product rule is u times the derivative of just the second factor, so v prime, plus v, so the original second function, times just the derivative of the first function. So uv prime plus vu prime. So we're taking the derivative of each piece, but not multiplying those answers together. We're multiplying the original first function times the derivative of the second function, plus the original second function times the derivative of the first function. So let's use the same function and see if we can come up with the same answer by the process of the product rule. So in this case, u is the x and v is the x squared plus 4. So u equals x and v is x squared plus 4. U prime is 1. The derivative of x is 1. V prime is x squared plus 4. V is x squared plus 4, so v prime is 2x. So using the product rule, u times v is u times v prime for this first part is x times 2x, plus, then we do the second part, v times u prime. So the original v is x squared plus 4 times u prime, which happens to be 1. So I didn't need the parentheses. So f prime of x equals 2x squared plus x squared plus 4. And continuing to simplify, I get 3x squared plus 4. That's the same answer we got by using distribution first before we took the derivative. So we see that the product rule works. I'm not going to go through a proof of how it works for every function, but there's just an example of one function where it works for. Now just take my word for it. You'll get into higher math classes where you can prove this, but right now we're just going to start using it. So you do have to memorize that product rule. And then we have the quotient rule. Up until now, when we've had something like this, we could rewrite it as x squared over x plus 4 over x, and continuing to simplify it. Now we haven't taken the derivative, we're just simplifying. If we cancel the x squared over x, we get x, and then we rewrite 4 over x because we didn't know up until this point a quotient rule. We're going to have this new function, which is the exact same thing as this one, and now we'll take the derivative of it. The derivative of x is 1 plus, and the derivative of 4 times x to the negative 1 is 4 times, and then you pull that negative 1 out in front, and then times x to the, subtracting 1 from the exponent, we get negative 2. Rewriting that, we get 1 minus 4, and only the 4 is over the x squared, because an x to the negative 2 means we're in the denominator, but the 1 didn't have a denominator. So that's our final answer, or we could get a common denominator if we wanted to. Our common denominator would be x squared. So multiply this by x squared and multiply this by x squared. So if we continue to simplify, we'll have x squared minus 4 all over the common denominator of x squared. You can leave your answer like this pre-common denominator, that's fine, but make sure you know how to get it to look like this because multiple choice answers might match this. So now let's look at the quotient rule. It's a little bit more complicated than the product rule, but it will come in handy for things that we can't rewrite. So the derivative of something divided by something, u divided by v, again, u is a whole function, not just a constant, it's something with a variable in it, and v is also something with a variable in it. If you have a constant in the top or the bottom, just rewrite your function. That's a lot easier. The derivative of u divided by v is v du. Now du is just another way of writing derivative of u. So we could write this v times u prime minus u times v prime all over the original function v squared. But v du minus u dv all over v squared kind of flows off your tongue a little bit easier. If you want to think about the upper function and the lower function, low d high minus high d low all over low squared kind of is something that has helped kids in the past. Remember the quotient rule. Find a way to memorize it. Say it a lot, sing a song about it. This low d high minus high d low, there's a great song that goes along with The Sound of Music. If you want to hear about that, let me know. But just find a way to memorize the quotient rule and the product rule. So let's use it here. U is always the numerator, so x squared plus 4, and v is the denominator, so we put x there. Then we need u prime, or du, and the derivative of x squared is 2x, and the derivative of 4 is 0. V prime is going to be 1. So I have v for my derivative. I'm ready to take the derivative now. I've done my setup. V times du, or u prime, minus u times v prime. Again, I didn't need the parentheses in this case. All over v squared, the original v, the original denominator, squared. Simplifying, I get 2x squared minus, now that those parentheses actually were important for this distributing here, minus x squared minus 4 all over x squared. Continuing to simplify, combining like terms on the top, I get 1x squared minus 4 all over x squared. Hey, that's the same thing as we had here. In this case, we didn't have to get a common denominator. It ends up being written with a common denominator already. So if I were doing this problem, I would still do it this way, simplify it first and then take the derivative of the pieces, because the quotient rule is a little bit more tedious to do, but your choice. So let's find the derivative of y equals 1 over x two ways. One way is to rewrite the original function to x to the negative 1 and then take its derivative. So multiply the negative 1 out in front, subtract 1 from the exponent, and then simplify. Okay? But I could use the quotient rule. So in this case, u would be the numerator, v would be the denominator, and I'll show you why this is kind of pointless. Whenever you have a constant in place of one of the letters, in place of one of the functions, the top or the bottom, the derivative of u prime is 0, because the derivative of every constant is 0, and the derivative of x would be 1. So our derivative would be, I'll use the low d high thing, low d high minus high d low all over low squared, or v du minus u dv all over v squared. Now, does the order matter with the quotient rule? Yes, it's very important because of this minus sign. So make sure that you have them in the right order. And do I have them in the wrong order? Sorry, I do have them in the right order, but what is x times 0? Of course, it's 0. And then 1 times 1, so we have 0 minus 1. So that is negative 1 over x squared. So you get the same answer, two different ways. You pick. I just think this first one's easier, more elegant. So let's find the derivative of the following using the quotient or the product rule. Notice we cannot distribute this. X times sine x, you can't multiply them together. So we have x as one function and sine x as the other, and it's a product, so we know we're going to use the product rule. So u is the x and v is the sine x. So we're practicing our product rule. U prime is 1, v prime is cosine x. The derivative, now that we've got the setup, is u times v prime plus v times u prime. Now with the product rule, the order really doesn't matter. As long as you do the derivative of one times the original plus the derivative of the other times the original of the other function, then you're fine. Because when you're adding, the order doesn't matter. So there's our derivative. However, when you're subtracting, like in the quotient rule, the order does matter. Okay, here we've got a combination of things going on. Notice this part is a function with an x in it, and this part is a function with an x in it. So we've got a product. This, however, is not a product because we have a constant times a function. So we can do that all as one derivative. And then when we're done, we're going to subtract the two answers. So just setting up the product rule for the 2x times cosine x, you're going to have to keep organized and make sure your work is neat so you know where things are. This is going to be the derivative of the 2x cosine x. So this side work over here. U prime is 2, v prime is negative sine x. So the derivative of 2x cosine x is u times the derivative of v plus v times the derivative of u. To simplify that, I have negative 2x sine x plus 2 cosine x. I notice some of you are in the habit of not writing parentheses or not writing the number, or the variable after sine or cosine. Those are very important. And then we're going to take the derivative of the 2 sine x. So our full derivative is negative 2x sine x plus 2 cosine x, which is our answer from over here, so that's the derivative of this part, minus, and then I need the derivative of 2 sine x, which is 2 cosine x. Combining like terms, my final answer for derivative is negative 2x sine x, because the 2 cosine x minus 2 cosine x adds up to 0. The next example looks a little tricky. We've got 3 minus 1 over x plus 5. If I want to, I can rewrite that top to be 3 minus x to the negative 1 over x plus 5. But that's all I can do. I can't separate this fraction because I have an x plus 5 in the denominator. I could get a common denominator in the top and then get that all to be one fraction, but I think this is a little easier here. So I'm going to set up my quotient rule. The top, is 3 minus x to the negative 1. And the bottom is x plus 5. So u prime, 0 minus, multiply by negative 1, and then subtract 1 from the exponent. So that simplifies to positive 1 times x to the negative 2. Here we have v prime. The derivative of x is 1, and the derivative of 5 is 0. So v prime is 1. So now I'm ready to write out the derivative. That was just preparatory work. I take the denominator, v, times u prime, minus u times v prime, all over v squared. Looks a little complicated. Scratch out or brush off the dust from all of your rules from Algebra 2 on how to deal with exponents. When I distribute that through, I'm going to add the exponent of negative 2 plus 1, so that's going to be x to the negative 1, because 1 plus negative 2 is negative 1, plus 5x to the negative 2, and then that negative distributes, so negative 3 plus x to the negative 1, oops, that's a 1, all over x plus 5 squared. Do not multiply out the denominator. We're still not multiplying out the denominator. So rewriting x to the negative 1, we've got 1 over x. Rewriting 5x to the negative 2, we've got 5 over x squared, minus 3, and then plus 1 over x again. So we can't leave it with a complex fraction like this. So let's get a common denominator on the top. let's use x squared. So multiplying this